All right, so this is just Amazon here. If you can pull that out. Yep, so this is just Amazon, and here you can see there's plenty of options, but just a cheap CNC machine such as shown here for $400, or there's even smaller ones for $150. These could be used to essentially secure the ceramic magnet or permanent ceramic magnet, and using the right bit, you would just put it into a computer program, a 3D CAD program, that you mapped out what size and shape you need for that that magnet, and you could run it through there and it would cut it for you, and your part is ready to go.
Okay. Interesting.
Now,
Darren Baxter says, even without friction, could there be heat generated from the rotation of the main crankshaft at high RPM?
that depends how high the RPMs are. The easy answer to that question is yes. The more realistic question to that answer is that you would need to be at many hundreds of thousands of RPMs, whereas a regular motor typically runs up to 10,000 RPMs. A Formula One car runs up to 15 to 18,000 RPM. So this is going to run a very high RPM before you would ever encounter any kind of heat resistance based on the magnetic repulsion. You would, however, have winding resistance in the alternator, and that is going to be based on your material sciences and basically your construction methods. So, of course, if it is getting hotter at a higher RPM due to winding resistance of the alternator, and I know I'm getting a little technical, so this might go over people's heads, don't worry about it. Essentially, you would be able to create a system to gap that alternator further from the winding resistance so that you lower that temperature should it get up to that temperature, but then you may be creating less electricity. That all comes down to tuning and the material science properties.
Right.
Some folks asked
if you could,
some folks asked if you could share the link for the magnets also.
Yep. So there's many.
Oh, sorry.
Yep, there's many different options there, and I would say you are going to have to shop around a little bit, but my primary source I would use is Grainger. Grainger is an industrial supplier that is available throughout most of the U.S. If you are outside the U.S., I apologize. I don't know the best places to source things for you, but you would have to do a little bit of research and find comparable places to shop.
And the machine that cut it, you called it a CNC machine?
Yep, CNC.
CNC, Cat Nancy Cat.
That's
machine.
Right. Yeah, Cat
Okay.
Nancy Cat.
All right.
Yep.
All right. Sorry, Simon.
Oh, it's okay. A question on rotation.
Yep.
How can you first off increase the rotation?
So
how would that be done?
We'll kind of get to that, but I don't want to answer that yet. Just
okay. All right, a little premature. Shocker.
Yeah.
And then one other thing is so the beginning of the first slide that you were showing, the actual all the pieces are to that. How does one get those types of pieces? Like what are they? Yeah, so what are they looking for?
Yeah, so if you want to pull up the slide again there, I'll kind of so I can point that out. So yeah, if you were trying to get this body or you were trying to do the base plate, so you could actually build these out of almost anything. You would just want it to be non-magnetic so that you're not interfering with the permanent magnets or the rotation.
So stainless steel, like stainless steel,
steel,
tungsten.
Yep, aluminum would actually be kind of the preferred cheap source.
Yep. And it's a good heat resistance too. Yeah,
yep.
Makes sense.
And alternatively, you could 3D print this in many different materials, PLA, PGA. Now, if you do 3D print it, I will only caution that there is warping that can happen with a 3D print, and that's just based on temperature, not necessarily temperature produced by the motor, so much as temperature ambient to your print. So you may have some dimension issues if you do that. But as far as just prototyping, I highly recommend doing it on a 3D printer first before you go and CNC a 30 centimeter block of aluminum.
Could you do it with wood? Darren Baxter wants to know if you could do it with wood, and then he says wood warps, which is true.
You technically could do this in wood, and various different types of wood could be practiced with. Wood warps differently depending on the grain and depending on the type of wood, or you've got your hardwoods and your softwoods and your very dry woods and your very wet woods and things of that nature. I am not a carpenter, but I'm sure if you are a carpenter, you would probably be able to choose some heat resistant wood that would be a good fit for this application.
So back to the dimensions real quick. We're talking basically like 29 inches wide OD or outer diameter, sorry, and then
right? So I actually do it all in metric.
I mean 11. It's 11 and yeah. You did 29 centimeters, so we're talking almost 11 and a half inches outer diameter, correct? Right.
Yeah. So it's not very big in this, but this is completely scalable. So now, of course, I designed these in a 3D CAD program called ShapeR 3D. With that, you could simply scale it to any percentage of what you want. And if you could build this small enough to go inside of a wristwatch, obviously a wristwatch has many complex moving parts. And if you're someone that manufactures wristwatches, you would probably be able to build this design into a wristwatch and make it effective. I don't have anything to tool at that scale. So I've chosen this scale as the most easy to work with for my purposes. But it all depends on what you want to apply it to.
Okay. Yeah, I was curious about the initial size, but general, workability, easy to do at home. That makes perfect sense. No bigger than 12-inch round. Easily to work with, small enough to be small, but big enough to still be able to see how things work and function before you scale up or scale down. Well done. Continue.
Yep.
I'm taking notes.
All right. So now on top of that partial crankshaft, I have a rotating assembly. Now remember that the partial crankshaft had a permanent magnet on top of it. So the bottom of this rotating assembly, which you can see over here on the blueprints, also has a spot for a permanent magnet, which is an opposing force. And so it is free floating again without friction on top of this portion of the crankshaft. And then we have these 8 vertical pylons that will also be surrounded by permanent magnets.
What's a pylon?
These vertical posts that are on the rotating assembly.
Boone wants to know, how strong of a magnet are we talking about?
So you're going to want the magnet to be strong enough to hold everything in place. And then you're also going to want to consider the weight of the material that you use in your rods and your pistons, so that you know how much torque you're putting into it at what speed, so that essentially you're not hitting those magnets against each other. The idea is to make it rotate freely without ever having any kind of friction or contact between any of the opposing magnetic forces. So
I'm sorry. Oh, sorry. I was going to say, I'm sorry. Crypto Ace has a question, but I can't find it.
He wants to know about Banca, but it's not really relevant to this conversation.
I didn't see it. Okay.
Wah.
Another case.
Okay, sorry about that. Okay, so the pylons, and I'm sorry if I missed this because I was looking for the question. The pylons in the red, are those magnets around the pylons?
Yep. So you would have a metal core here that can accept a round cylindrical magnet over it.
Inside the shaft. Yep.
Yep.
How the heck do you get I've never seen a magnet with
Yep.
a with.
So that is why it's important to be prepared to machine or CNC cut your own magnets and your own shapes, because if you don't, you're not going to have an easy time completing this design by any shape of magnet that currently is, market ready and available. They're generally just not very accommodating for this application. So you will want to make a more custom fit, which means you're going to want to have a little bit of tooling available to you.
Could you you could buy those round magnets like that, could you get the round magnets and then like punch a hole through it
if you wanted to try that, as all things with science and manufacturing and do it yourself, just be prepared to fail a little bit. But
I mean, I was just thinking, like, you can get those round ones, and then even if they weren't as thick or as deep as you needed, like you could like stack one or two on top of each other.
As long as you're able to achieve the principle of having a cylindrical magnet that gives a force in a outward direction, and putting another cylindrical magnet around that gives a force in an inward direction, then you've achieved the intent, essentially.
I mean, already I'm thinking to myself, if I'm going to try to build this, my first challenge is the magnet, and because if you can't make these magnets to go on these pylons, then that's like the first step in my mind of what I need to see if I could even do it, to make the magnets.
And it's probably every dad's trope out there for his son, but the right tool for the right job. So I'm not saying you can't do it by punching holes or other things like that, but you'll probably be best served to be prepared to spend the money on the tooling that will do the job, certainly, and then do the job as concretely as possible from the get-go.
So what tool would do that then to make
the
pylon?
CNC machine would be the best for this.
Oh, okay.
Yeah.
All right. So that same CNC machine can make this kind of magnet. All right. I thought that was going to have to be something separate. Okay.
Yep. You can certainly do all the magnets for this design on a single CNC machine like that.
Awesome.
Mm-hmm. Mm-hmm. Yeah.
Okay.
Not bad for $400.
Yeah, not bad at all. So going on to the next one. So now I added a few different visuals in this single slide here, but essentially what we did was we took our piston rods. Our piston rods are connected through a shaft there to our pistons themselves. And the piston rods are being placed over the vertical pylons that have those permanent magnets. Yep. And there's a permanent magnet inside the piston rod. And this is essentially replacing what is a bearing in a traditional engine with a magnet. Not to be confused with magnetic bearings, because that's a different thing. There are magnetic bearings out there, but they do make contact. They're not friction free. So just to make that clear, you're making your own magnetic bearing that has full magnetic propulsion and no contact.
Okay.
Now, then you're going to take the second half of the rotating assembly here, and you're going to connect that to the lower half of the rotating assembly. And then you would drop in the upper half of the crankshaft through that upper half of the rotating assembly. Now, you'll notice that the lower half of the crankshaft has a square vertical connector. Of course, that means square peg, square hole in this case, and that minimize rotation. And then you'll also notice that the crankshaft coming vertical from the second half, it's turned at 45 degrees. And I'll point out why that is in a little bit here.
Okay.
Now, on the pistons themselves, we have a piston ring, and we have a flat disc permanent magnet at the tip of the piston. So now, at this point of the motor, we have nothing electrical added to it whatsoever. This is simply permanent magnets and whatever base material you've used that is non-magnetic to provide a body, crankshaft, rods, piston, etc. Most likely aluminum if you're trying to do a more professional build for this. So we're only looking at aluminum and ceramic with a little bit of ferrous material in it right now. None of that is rare. None of that is hard to obtain, and none of that is hard to tool if you have the right tools. Any questions to this point?
I don't see any other questions in the chat right at the moment.
Okay. And I will just point out there is a piston rod clearance along the center line of all these pistons to allow for that rod to have full rotation without any kind of interference or friction.
Gotcha.
You'd have to make those you call them the piston. You have to make those too, right? So you'd have to. Can that machine do this? Make that as well?
That's correct.
Okay.
Yeah.
Okay.
Now, once
Sorry. Go ahead. Go ahead. Sorry.
Did you want me to go back to the last one?
No. I was gonna touch on the CNC machine. Like, I was just curious if Melissa, you've seen any type of machine cut out a pattern.
I really
Any
haven't.
machine.
That's
Okay,
why
okay.
that's why I'm kind of fascinated by this whole. I've heard of like 3D printing and all these things, and I don't really understand what that even is, to be honest with you.
So I'll show you. I don't know if you want to switch the screen there, but I got a couple. My whole closet of my office is two 500 millimeter 3D printers over there that do a lot of work. So, yeah, and the CNC lives in the garage, but it's messier.
Yeah, it is.
Simon knows. So once we've got it to this point, we're now putting the top plate on for this module, right? So we've got our closed module here, and we've put piston sleeves on. So the ring that is around the piston is creating magnetic propulsion against those permanent magnets that were surrounding each of the piston clearances. And then as the piston ring and the permanent magnet on the end of the piston goes through the piston sleeve, it's passing through a copper